So in this lecture, we want to discuss solution of equations in terms of basic solutions, feasible solutions, etc. So general linear programming problem stated as max or minimum z is equal to c1x1 plus c2x2 and so on cn xn subject to constraints. See here a11x1 plus a12x2 up to a1n xn less than or equal to or greater than b1. So see here constraints may be less than equal to b1 or equal to b1 or greater than b1. So this is the first constraint, second, third, and so on. So see here this is the bm means m constraints. So here m constraints, m constraints. And see here we want to maximize or minimize, and this is the objective function. Objective function means x1 greater than equal to 0, x2 greater than equal to 0, and so on, xn greater than equal to g1. These are the state variables which we want to find. You can say here these are state variable. State variables which we want to find. And this is the non-negative risk condition, non-negative, or you can say non-negative restrictions, non-negative restrictions. So or simply we can say here a simple linear programming problem can be written as maximize z equal to 10x1 plus 12x2 plus 15x3 subject to constraints. These are the constraints. Here three constraints with x1 greater than equal to 0, x2 greater than equal to 0, and so on, means x3 greater than 0. So you can say this is the linear programming problem, and here this is the objective function I want to maximize. And here there are three constraints, and this is the non-negative restrictions, means all state variable should be positive. Now we can say here our motive is to find a solution of given problem. Means given problem means we want to find the solution of this problem. Means we want to find x1, x2, and x3 which maximize the objective function z. Here now we want to discuss some important points regarding solution of LPP, means linear programming problem. Suppose we have suppose we have a standard form of LPP is max z equal to c dash x dash transpose subject to constraints, means a dash x dash transpose less than equal to b dash transpose. with non-negative restrictions x dash t greater than equal to 0. So I can say this is the objective form. This is the LPP. One means standard form. Standard. This is the can say this is the standard form. So this is the matrix representation of linear programming problem, and where C dash equal to C1, C2, C3 and so on Cn. Can say these are the cost coefficients, and this is the cost coefficient, and A dash equal to, you can say here A11, A12, A1n, A21, A22, A2n up to AM1, AM2, AMN, and X dash equal to X1, X2 up to Xn, and B dash equal to B1, B2, Bm. Means we can say here this is the LPP with, we can say here this is LPP with M constants, and M n variables, n variables. Means this is the matrix representation of LPP with M constants and M constants and n variables. Now above problem can be written here, means object means LPP can be written here. So you can write here now above LPP, one can be written here, can be written here max Z equal to CX transpose subject to constants AX transpose equal to B transpose, and B transpose should be greater than 0 with X transpose greater than equal to 0. So I can write here this is the LPP2 means representation, different representation of 1. Also write here 2.1, 2.2, 2.3. Means 2.1 is the objective function and 2.2 is a constants, and 2.3 is x dash x transpose greater than equal to 0, means all state variable should be greater than 0. Where C is C1 comma C2 up to Cn 0 0. X equal to x1 comma x2 comma xn. Now xn plus 1, xn plus 2 up to xn plus m, and b equal to b dash means there is no change in b and b dash in equation in LPP 1 and 2. You can write here b1, b2 and bm, and a is, can write here a is a11, a12, a1n, a21, a22, a2n up to a m1, a m2, a mn, and here 1 0 0 0 1 0, and here 0 1. This is, you can write here, this is the identity matrix. Identity matrix. So we can say here, this is the LPP. We can say here, this is the LPP with n plus m variables and m constants. M constants. So see here, LPP1 can be written as LPP2. Now we want to discuss the solution of LPP. Means we want to find the state variables which maximize the objective function 2.1. So we can say here, solution of LPP. Solution of LPP means LPP 2. So write here, any set x, that is x1 comma x2 comma xn up to xn plus 1, xn plus 2 up to xn plus m. Any set x of variables is called the solution of LPP means linear programming problem. 2. If it satisfies the set of constraints only, means satisfies equation 2.1, means satisfy equation 2.1. So you can say here any set of variables is called the solution of LPP if only it satisfy the equation 2.2. Now want to discuss the point feasible solution. Want to discuss the point feasible solution. So feasible solution. So right here any set x, x1, x2 and so on xn, xn plus 1, xn plus 2, xn plus m of variables is called a feasible solution, is called a feasible solution of LPP if it satisfies the set of constraints 2.2 and non-negative restrictions, non-negative restrictions 2.3 also, means any set x you can say here it is the feasible solution if it satisfies the constraints 2.2 with non-negative restrictions 2.3 also. In the same way, we want to discuss basic solutions. Basic solutions. This is very important point. Basic solutions. So I can write here a basic solution. A basic solution of this basic solution to the set of constraints to be a basic solution to the set of constraints 2.2 is a solution obtained by setting any n variables, setting any n variables uh, setting any n variables equal to 0, equal to 0. Means you can write here among n plus m variables, set n variables equal to 0. Among n plus n variables, set n among n plus n variables, set n variables equal to 0, and solving for remaining and solving for remaining m variables, provided that the determinant of the coefficient of the coefficients of these m variables is non-zero, So we can say here such m variables are basic variables, and remaining n variables and remaining n variables are non-basic variables. Non-basic variables means these are zero valued variables. Zero valued variables. Zero valued variables. Maximum number of the maximum number of basic solutions. The maximum number of basic solutions are m plus n c m. M plus n cm, we can write here m plus n factorial upon n factorial and m factorial. So maximum number of basic solutions are m plus n cm. Now in the same way we want to discuss basic feasible solution. Basic feasible solution. Means a basic solution is, you can write here, a basic feasible solution is a basic solution. Means a basic feasible solution. Basic feasible solution is a basic solution which satisfy the non which is a basic solution which satisfy the non-negative restrictions. Satisfy the non-negative restrictions 2.3 also. 2.3 also. And basic feasible solution are of two type. So I can write here, basic feasible solution are two types. Two types. One is non-degenerate. Non-degenerate. Non-degenerate basic feasible solution, and second is degenerate basic feasible solution. Degenerate basic feasible solution. So can write here, degenerate basic feasible solution is a basic solution which has exactly, means can say here, non-degenerate non-degenerate basic feasible solution is a basic feasible solution which has exactly m positive xi's, or we can say r m basic variables are positive, or m basic variables are positive, and remaining n variables are zero valued. Now we can say degenerate basic feasible solution. So we can say here, degenerate basic feasible solution is basic feasible solution. Means degenerate basic feasible solution is a basic feasible solution if one or more basic variables are zero valued. One or more basic variables are zero valued. value. For example, all these solutions we can explain through examples. So first example is, we can say, means this is the problem when my z is equal to 3x1 plus 4x2 plus 7x3 subject to constraints 2x1 plus 3x2 plus 4x3 equal to 5, and 3x1 plus 4x2 plus 5x3 is equal to 6. So we can say here total variable means m plus n. We can write here n plus n, n plus m means total variable is 3 and number of constraints is 2. So maximum number of basic solution are m plus n factorial upon n factorial into m factorial. So 3 factorial means here n is, we can write here total variable is m plus n. So I can write here 2 factorial into 1 factorial. So we can say 3. So total number of maximum solution is 3. So we can write here x1, x2, x3. So for finding the solution, put m variable equal to 0. Put m variable equal to 0. So I can say here means put x1 equal to, first put for means for first solution put x1 equal to 0. So see here get 3x2 plus 4x3 equal to 5, and 4x2 plus 5x3 equal to 6, and simplify this. Here we get x1 equal to -1 and x3 equal to 2. Again, for second solution put x2 equal to 0. So here get for x2 equal to 0, 2x1 plus 4x3 equal to 5, and 3x1 plus 5x3 equal to 6, and simplify these two equations, get x1 equal to minus 2 and x3 equal to 3 upon 2. Similarly, for third solution, put x3 equal to 0. So equation becomes, for x3 equal to 0, equation becomes 2x1 plus 3x2 equal to 5, 3x1 plus 4x2 equal to 6, and simplify, get x1 equal to minus 2 and x2 equal to 3. So we get these three solutions, and see here, this is the as we know that for feasible solution all state variables should be positive. So we can say here, due to negativity, this solution is known as infeasible. Means you can say nature of solution. So infeasible, and this is also infeasible, and this is also infeasible. And you see here, as all basic variable are means has solution. So we can say here non-degenerate, means all basic variables is non-zero valued. So you can say all solution are non-degenerate. All solutions are non-degenerate basic non-degenerate basic infeasible solution. Basic infeasible solution. Now we want to discuss one more problem, means find the all basic solutions, means basic solutions and infeasible solution. So no need to write non-negative restrictions. So this is the problem. Now we can see here number of variables, that is n plus m equal to 4, and number of constants is 2. So total number of basic solution is 4C2, means 4 factorials, 2 factorial and 2 factorial. So get 6, means here we get 6 basic solution. 6 basic solution. So here there are 4 variables, so write here, means x1 x2, x3, x4. And first solution, second, so right here, means first, second, third, fourth, fifth, and sixth. So if you put first, means here there are means there are two constraints. So put two variables for finding solution. Put two variables as equal to 0. So first write x1 equal to 0 and x2 equal to 0. So equation becomes, say, 2x3 plus x4 equal to 3, 4x3 plus 6x4 equal to 2. And if we simplify, we get 2 and minus 1. Similarly, for second solution, put x1 equal to 0 and x3 equal to 0. So for second solution, x1 0 and x3 0. So equation become 6x2 plus x4 equal to 3 and 4x2 plus 6 x4 equal to 2. And if we solve this equation, get x2 equal to half and x4 equal to 0. Similarly, for third solution, put x1 equal to 0 and x4 equal to 0. x1 equal to 0 and x4 equal to 0. Sorry, for third solution, so right here x1 0 and x4 0. So equation becomes 6x2 plus 2x3 equal to 3 and 4x2 plus 4x3 equal to 2. 4x3 equal to 2. So if we solve this equation, simply get x2 equal to half and x3 equal to 0. Similarly, for fourth solution, put x2 equal to 0 and x3 equal to 0. x2 0 and x3 0. So equation become 2x1 plus x4 equal to 3 and 6x1 plus 6x4 equal to 2. And if we solve this equation, simply get x1 equal to 8 upon 3 and x4 equal to minus 7 upon 3. Similarly, For fifth solution, put x2 equal to 0 and x4 equal to 0. x2 0 and x4 0. So right here equation become 2x1 plus 2, x3 equal to 3 and 6x1 plus 4, x3 equal to 2. And if we solve these equation, simply get, see here, this solve this equation, simply get x1 equal to minus 2 or x3 equal to 7 upon 2. Similarly, for sixth solution, put x3 equal to 0 and x4 equal to 0. So equation become, see, sixth solution 2x1 plus 6x2 equal to 3, 6x1 plus 4x2 equal to 2, means 2x1 plus 6x2 equal to 3, 6x1 plus 4x2 equal to 3, and if we solve these equation, simply get x1 equal to 0 and x2 equal to half. So now we want to discuss the nature of all these solution. So nature of solution. So for first solution is get one variable is negative, so we can say here infeasible solution. So first is infeasible and fourth is also infeasible and fifth is also infeasible solution. And see here, for first means we put x1 x2 0, get means x3 and x4 are non-zero valued. So we can say here this is non-degenerate, means first solution is non-degenerate. Non-degenerate basic solution. Non-degenerate basic solution. Similarly, fourth, if you put x2 and x3 0, rest variable are non-zero valued. So you can say here it means fifth is non-degenerate and means fourth is also non-degenerate basic solution and fifth is also non-degenerate basic solution. So you can see here this is also non-degenerate and this is also non-degenerate. So you can say here first, fourth and fifth are infeasible solution, infeasible non-degenerate basic solution, non-degenerate basic solution. Now see first now we want to discuss the nature of second solution. Second solution So see here, second solution is means all are positive. So you can say here basic feasible solution. Basic feasible solution. And here see, if you put x1 0, x1 equal to 0 and x4 equal to 0 and get one variable is 0 valued, means x3 is 0 valued. So we can say here this is basic feasible and degenerate solution. Degenerate solution. Similarly, we can say here third solution for third solution. Third is also in third. All variable are positive. So you can say here basic feasible solution and put two variable equal to 0. Get one variable is 0 valued. So this solution is also degenerate solution. Similarly, sixth solution and sixth solution is also basic feasible solution and degenerate basic solution. So finally you can say this is the solution and nature of above problem. So we'll stop here. Thank you all.